adiabatic process is useful in the construction of heat engines? A. How this process does work since there is no heat exchange in the system. B. How do you distinguish isothermal and adiabatic curve in same PV plane? C. What type of work is performed in adiabatic expansion, positive or negative? So let us discuss question A, okay? Now we know in adiabatic process, no heat enters or leave the system, okay? So I'm writing in adiabatic process, no heat enters or leave the system. Therefore, in adiabatic process, delta Q equals 0. So we have this, okay? And in adiabatic process, the internal energy, okay, we denote it by the symbol delta U of the system always or let me write, okay, it always changes, okay. So we have this. Now we know from first law of thermodynamics, okay, so I'm writing first law of thermodynamics, okay. We know from first law of thermodynamics, delta Q equals delta U plus delta W, okay. So we have this. Yeah, we have this from first law of thermodynamics. Now, as delta Q equals 0, therefore, from this equation, okay, we are going to use this equation. Therefore, we can write delta U plus delta W equals 0, or we can write delta U equals minus delta W. So we have this, okay, we have this. Now, for adiabatic expansion, okay, so for adiabatic expansion, work done, okay, delta W is positive. So this is positive, okay. So we have this. Therefore, from this equation, delta U, okay, this equals minus, and we have positive work done, okay. So we have this. Clear? So what we get? Delta U equals minus delta W. So it means that internal energy, okay, this decreases. So we find this, okay, delta U or internal energy is negative. So it means that internal energy decreases. Okay. So if internal energy decreases, so we find temperature decreasing. Okay. Or temperature also decreases. So we have this. Clear? So we have this. So when we have an adiabatic expansion, okay, then we find internal energy decreases and the temperature also decreases. So we have this, okay. And we need to note for adiabatic expansion, work done is positive, okay. So we have this. So this represent work done, okay. This represent work done. So this is to be noted, okay. So from question C, okay, what type of work is performed in adiabatic expansion, positive or negative? So we are getting the answer for question C also. When we have an adiabatic expansion, okay, then the work done is positive. So I'm going to discuss it later also. Clear? Now, we can write in this way, okay, since no heat is added to the system, okay, no heat is added. So if no heat is added, okay, then any energy transferred, okay, or converted, transferred out as work. Clear? Any energy converted or energy converted to work must come from the system internal energy. So we have this. Due to this, the temperature of the system falls. So due to this, the temperature, okay, the temperature of the system fall. Clear? Or false. So we have this. So this is to be noted, okay. Now for adiabatic compression, okay, so we next go for adiabatic compression. For adiabatic compression, now we have this, okay, delta Q equals 0 for adiabatic process. So from first law of thermodynamics, okay, we can write thermodynamics. We have this, okay, delta Q equals delta U plus delta W. So we get this 0 equals delta U plus delta W. So we can write delta U equals minus delta W. So we have this. Clear? Now what do you find? Let us call it equation 1. But we know work done, okay. So as I said earlier, this is work done, okay. This is work done. And we know work done equals P times delta V. So we have this, okay? Pressure times change in volume. Now for compression, okay? For compression, delta V, that is change in volume, is negative. So we have this. For compression, okay? Delta V is negative. Therefore, work done, that is delta W, is negative, okay? This is for compression. So we have this, okay? We have this. So we got, or we have the solution for question C, okay? So what type of work is performed in adiabatic expansion, positive or negative? So when we have, let us discuss solution of this, okay? Solution of C for adiabatic expansion, okay? For, I'm writing in this way, for adiabatic expansion, work done is positive. So we have this is positive. And for adiabatic, okay? And for adiabatic compression, okay? Compression, work done. So we have this, okay? Work done is negative. So work done is negative. So we have this. For question C, okay? This is solution for C. Now, let us come to this, okay? Now, from 1, okay? Delta U equals minus, and we know work done, delta W is negative. So we have minus delta W, okay? Therefore, we get delta U equals plus, that is positive, work done. So we get this, okay? We are getting this. So what we find in case of adiabatic compression is that internal energy increases. So I'm writing over here, internal energy increases, okay? We have discussed earlier in adiabatic process, okay? The internal energy of system always changes. So we can see, okay? In adiabatic process, internal energy decreases for adiabatic expansion and internal energy increases for adiabatic compression. So we have this, clear? Now I'm writing, therefore, internal energy, okay? So therefore, internal energy, okay, increases, and the temperature, okay, and the temperature increases. So we have this. Now, since we are discussing adiabatic compression, okay, so what we find, if no heat, okay, we are compressing the system. So, and we know in adiabatic process, there is no exchange of heat between the system and the surrounding. So, if no heat leaves, okay, so if no heat leaves during compression, okay, then work done on the system, okay, we are compressing, work done on the system must be added, okay, it must be added to its internal energy. So, internal energy and the temperature, okay, and the temperature of the system of the system increases. So we have this. Clear? Now, let us go for question B, okay? How do you distinguish isothermal and adiabatic curve in same PV plane, okay? So, I'm writing question once again, okay? How do you distinguish, okay? Distinguish isothermal and adiabatic curve in same PV, that is pressure volume, okay, plane. So we have this question, okay. Now, let us discuss this, okay. We know, so I'm writing slope of adiabatic curve, okay, equals gamma, okay, this is gamma times slope of isothermal, so slope of, let me write in this way, okay, slope of isothermal isothermal curve. So I'm writing in this. So we have this. And what we find is that gamma is greater than 1, okay. We find this. The value of gamma is greater than 1. Therefore, we find slope of adiabatic curve is greater, okay. So this is greater than slope of isothermal curve. So we find this, okay. So this is the concept. This is the concept, okay. We are going to use and discussing this question. So we find the slope of adiabatic curve is greater than the slope of isothermal curve. So we are going to use this concept. Clear? So from this concept, okay, we can tell adiabatic PV, that is pressure volume curve, okay, is steeper. It is steeper than the corresponding isothermal curve. So we have this. So let's understand this with reference to the diagram, okay? So let's say we have this, okay? PV diagram. So we have this. Now let us consider isothermal expansion and adiabatic expansion, okay? So we know in case of expansion, the volume increases, okay? So we are going to start from this pressure, okay? So this is V1 and we have volume V2 over here. Clear? So we find this. So we find this, okay? What we find is that pressure corresponding to this point, let's say this is P1, okay? And volume corresponding to this point is V1 and volume corresponding to this curve, okay? This curve, this is called isothermal. And this is called adiabatic, okay? This is adiabatic curve. So we have isothermal curve and adiabatic curve in the same PV plane. And we have isothermal expansion and adiabatic expansion because volume is increasing, okay? We can see from the graph, volume is increasing from V1 to V2. So we have this. Clear? So what we find in this case, okay, we find adiabatic curve is more steeper. We can see it is more steeper. This is adiabatic curve, okay, and it is more steeper in comparison to isothermal, okay. When we have adiabatic expansion and isothermal expansion curve in the same PV plane, okay. So we find this. So this is to be noted, okay. And what we note from the graph is that, okay. So let me erase this. So let me write. This is more steeper, okay. And this is less steeper. So we have this. Clear? And what we find from this curve is that, okay, we find area, okay, area under isothermal. We find area under isothermal process is greater or is larger, okay. So let me write in this way. We find this area under isothermal process is greater or is more in comparison to area, okay, in comparison to area under adiabatic process. So we have this. Clear? So as I said earlier, we have this for adiabatic expansion and for isothermal expansion, okay. So we have this condition. So this is to be noted, okay. So if we have this, then what we find, we know area under the curve in PV diagram gives work done, okay. So we can write, therefore work done, okay, in isothermal expansion, okay, is greater than work done during, so let me write this way, okay, work done during adiabatic expansion. So these are very important concept, okay, to be noted. So we need to note this, okay. Now this is isothermal expansion, or it is isothermal curve, okay, and this is adiabatic, okay. This represent adiabatic expansion. So what conclusion can we draw looking into this PV diagram is that, okay, when we have expansion, okay, so I'm writing for adiabatic and isothermal expansion, we find adiabatic curve, okay, lies below isothermal curve. So we have this. So as we know, this curve, okay, this curve is more steeper and this curve is less steeper. So we have this. So this is to be noted, okay. Now let us discuss or have some concept, okay, extra concept, okay. So extra concept, so I'm giving you the extra concept. Clear? Let's say we have adiabatic compression and isothermal compression. Adiabatic compression and isothermal compression. So we want to discuss this using the PV diagram, okay. So we have a PV diagram. Now we have compression, okay? So the volume decreases. So we need to understand this, okay? Now what we find is that, okay, in this case, let's say we are starting from this point, okay? This is the initial. So we know in case of compression, volume decreases, okay? So we have this. So this represent the PV diagram for adiabatic and isothermal compression with adiabatic curve, okay, above the isothermal curve. So this is isothermal curve. So we find this. So I'm writing over here. Clear? So what we find, adiabatic curve is more steeper, okay? It is more steeper. And isothermal curve is less steeper. Looking into this PV diagram, okay? So I'm writing adiabatic curve is steeper, okay? It is steeper than isothermal curve. So we find this, okay? So adiabatic compression curve, okay? So we can see adiabatic compression curve is above the isothermal curve, okay? So adiabatic. So we find adiabatic compression curve lies, okay, above, it lies above isothermal compression. So we have this curve. So we can draw conclusion that, okay, work done, we know in PV diagram, okay, area under the curve in PV diagram gives the work done or work. So what we find, work done in adiabatic compression is greater than work done in isothermal compression. So we need to note this, okay, when we have adiabatic compression and isothermal compression. Now let us discuss this also, okay? Let's say the system, okay, expand, or the system is expanding, okay, expanding adiabatically from initial volume V1 to V2, and then compressed, okay, isothermally, okay, compressed isothermally to V1. So that is V1 is initial volume, okay? Initial volume. So here we can see the system is expanded adiabatically. So we have adiabatic expansion and is compressed isothermally. So the PV diagram will be of this type, okay? So what we can see, we have adiabatic expansion, okay? So we know in case of expansion, volume increases, okay? So I'm starting from this point, okay? Clear? So we have pressure P1 corresponding to volume V1, okay? So this is the adiabatic expansion, okay? Adiabatic expansion, we can see volume is increased from V1 to V2. So we have this. Now we have isothermal compression, okay, to V1. Clear? So what we find is that, okay, in isothermal compression, okay, from V2 to V1. So we have this. So this curve represent isothermal compression. Okay, it represent isothermal compression. So let us put the value of pressure also, okay? So the pressure is P2 corresponding to V2, okay? And let the pressure corresponding to this, that is this point of isothermal curve be P3. So we have this when we have adiabatic expansion and isothermal compression.